Sigma and pi bonds are a type of bonding used to explain observed phenomena in molecules. Again, it's a sigma and pi bonding. This is a model used to help explain some of the bonding arrangements that have been observed in different types of molecules, primarily used for explaining how double and triple bonds form in molecules. Let's start using a molecule of ethene, which has two carbons that contain a double bond between the carbon atoms. Start by focusing on the carbon atom on the left. This has 1, 2, and we have 3 things attached to the carbon atom on the left. Consequently, our carbon atom on the left would use a hybridization scheme of sp2 to hold the 2 hydrogens in 1 carbon atom in its bonding arrangement. Remember, our sp2 designation tells us that we have 1 s orbital and 2 p orbitals that have been blended together or hybridized to create the sp2 hybrid orbital. Now, if we recall, the p sublevel, though, contains 3 orbitals in our p sublevel. Consequently, what we can say is that one of the p sublevel orbitals was left out of our little blender and was not hybridized. So we have a p sublevel orbital that's still a p orbital that's not part of the sp2 hybrid scheme. It's this non-hybridized p orbital that's utilized in our bonding arrangement to make the second bond in our double bond. So the p orbital that did not get blended or hybridized is utilized to make the second bond in a double bond. Let's focus on one of the carbon atoms in our structure, where we said it has an sp2 hybridization scheme. The orbital geometry in this would be trigonal planar with 3 equally spaced orbitals. We have covalent bonds forming, the sharing of electrons between our 2 bonded carbon atoms, and we also have covalent bonds forming between the hydrogen and carbon atoms in our structure. The type of bond we see here between our carbon atoms and also between the carbons and hydrogens is a bond type that's known as a sigma bond. This type of covalent bond is a very strong type of bond for a couple reasons. One reason is we have complete overlap of the bonding orbitals along what's called the bond axis. For the bond axis, just imagine a shish kebab skewer running through both atoms that are bonded together. That would be what we refer to as the bond axis. Another reason a sigma bond is very strong is that the bonding pair of electrons is essentially trapped between the 2 nuclei. The 2 carbon atoms isolate this pair of electrons and hold those electrons exclusively between those 2 atoms. So this pair of electrons, the bonding pair, since it's isolated between the 2 nuclei, that electron pair is held tightly by both bonding atom nuclei. So it's the 2 reasons that make a sigma bond fairly strong. One, the overlap of the electrons is directly along the bond axis running between the 2 bonding atoms, and the bonding pair of electrons is isolated or trapped between the 2 bonding nuclei and held tightly by the nuclei of both bonding atoms. Now, of note, in our covalent compounds, all single bonds are identified as being this variety type of bond known as a sigma bond. Take a moment and recall that our p sublevel is made up of 3 orbitals. All 3 orbitals have an identical shape, this sort of hourglass or dumbbell type of shape. The only difference being their spatial orientation, in that each of the p orbitals, one is located along the x-axis, one the y-axis, and one the z-axis in 3-dimensional space. We have our ethene molecule with all of its sigma bonds between our atoms in the structure thus far. However, our carbon atoms still have a p orbital that was not included in the blender to make the hybrid sp2 orbitals already being used in bonding. It's this unhybridized p orbital that's now utilized to make the second bond in our double bond. In this overlap, what happens is the edges of our cloud can slightly overlap above and below the bond axis of our sigma bond. This slight overlap of our unhybridized p orbital is a type of bond that's known as a pi bond. So this would represent a single pi bond and is our second bond, creating the double bonded structure. Now a pi bond tends to be weaker than what we see for a sigma bond in our covalent bonding structure. One of the reasons is that if we notice our bonding orbitals here for our making our pi bond, these bond orbitals are actually perpendicular to the bond axis between the carbon atoms. Because it's only the edges of the electron clouds touching, the overlap of the bonding orbitals is lessened compared to what we see in a sigma bond, and this contributes to a pi bond being slightly weaker than a sigma bond. Also, the bonding pair of electrons is not trapped between the nuclei of the bonding atoms. With the bonding cloud existing above and below the bond axis, the electrons in this cloud can move away from the nuclei of the bonding atoms. It's for these two reasons that the bonding orbitals are oriented perpendicular to the bond axis, so we only get a very light overlap of the edges of the bonding electron clouds, contributes to the pi bond being slightly weaker than a sigma bond. And secondly, that the bonding electrons are not trapped in between the bonding nuclei. So the electrons are a little more free to move than what we see in a sigma bond. Both of these contribute to a pi bond being slightly weaker than a sigma bond. In molecular structure, covalent bonds, all second and third bonds in double and triple bonds are what we know to be, or what we identify as being, pi bonds. Take a look at a molecule with a triple bond, ethyne C2H2. C2H2 has sp hybridization, so in this, two of the p sublevel orbitals were not hybridized. One of the unhybridized p orbitals makes a pi bond in this area. This would be one pi bond. The other unhybridized p orbital is at 90 degrees to the first p orbital, and we get an overlap out here, and we form a second pi bond, and that would be our structure for a triple bonded molecule with one sigma bond in the center and then two pi bonds surrounding that bond axis.